Hello everybody, this is Steven coming to you once again through the power of the internet, and today we are on day 2, if you want to call it that, of my radio frequency and microwave engineering introductory class note review. So if we want to recall from last time what we ended with, Z naught here, as well as we defined gamma, we defined capital gamma, which is our reflection coefficient, we defined the voltage standing wave ratio. At the very end, we ended up getting this equation right here, which is the relationship between the input impedance of some length of cable terminated by a load, right? So length, some transmission line of length L terminated by a load ZL with a characteristic impedance of Z naught. And we also talked about how the voltage and the current that's traveling down a transmission line is a sum of a forward propagating and a reflection electromagnetic wave. So these are just the major equations that we ended up defining last time. All right, so again, we have our transmission line of length L, right? And where this point here is Z equals 0 and going to the right is positive. So this is going to be in the negative Z direction. And if you've got some length and you hook up you want to find what the impedance looks like at this point here, looking down the transmission line terminated by ZL, we've got this equation right here. And if you take some limits, right, so if your load equals the characteristic impedance of your cable, your input impedance is going to be the same as your load impedance, right? So it doesn't change it. Which means that if you've got, say, for example, a 50 ohm characteristic impedance coax line terminated by a 50 ohm load, at any point away from the load, it will still look like a 50 ohm load, right? So Z in this case would just be 50. If we've got ZL equals 0, so a short circuit, you've got a function here. So your input impedance is going to be a function of how far away you are from the load. Okay, and if ZL equals infinity, so an open circuit condition, your input impedance is going to be another function of L and beta, of course. So what this means is that the impedance that you see actually changes with these trig functions here as a function going away from L. So we can actually use this property in order to do some cool stuff. So for example, the transmission line transformer. So if your load doesn't equal your characteristic impedance, but we have the condition such that the length that we're talking about, so L, is equal to your wavelength divided by 2, we have the condition, you will end up getting that your input impedance here, Zin, is equal to your load, okay? So if you've got a mismatch, right? If you attach the correct length of cable onto it for a particular frequency or for this particular condition, right? You will still have the input impedance equal to the load, right? Because if you just go through this, right, there exists a solution to these to this equation here that will get you the same answer. Okay, again, it's another thing that if you want, you can sit down, you can do the math and verify that if you so choose. But then what this gives you is, so for example, if you've got two different characteristic impedance transmission lines, right, and you've got ZL and you've got Z naught, and they're not equal to each other, okay? But you want to be able to connect them to each other and reduce the amount of reflections as much as you can. You're effectively using another piece of transmission line to transform the impedance that this transmission line will see. Right? So this transmission line sees Z in here as its load. Now Z in is going to be the total combination of Z1 and ZL, depending on the length of Z1 here, or of the cable that is represented by Z1. So if you satisfy these conditions, then it'll work. And if L is equal to lambda divided by 4, you've got Zn is equal to Z0 squared over ZL. So again, if we set L is equal to lambda dividing by 4, this gives us Zn is equal to Z1 over Z1 squared over ZL. So if you rearrange that, so Z1, so I should explain that this scenario right here is just the general case, and then using this specific example, we're doing it right here. So with this particular example, if we set L is equal to lambda over 4, so L is going to be the length of this piece right here, lambda over 4, this gives us Zn of Z1 squared divided by ZL, and if you rearrange that, it gives you a Z0 of Z1 squared over ZL for the matching condition. Okay, so Z1 is going to equal to the square root of Z0 times ZL all square root when L is equal to lambda over 4. So some of you may have heard of something called a scattering matrix. So with circuits, you can represent your blocks of circuits, if you want to call it that, as matrices. You can represent them as matrices. And there are several different types of matrices that you can use. So before we get to the scattering matrix, we need to build up the different types and the motivations that one would use at lower frequencies and whatnot. So this is still also review if you've taken university level circuits classes and whatnot. This is normally covered. So we're just going to briefly be going through that. So in low frequencies, we use the Z, Y, and ABCD matrices in order to analyze circuits. But in high frequencies, we use S, which is the scattering matrix instead. So the Z matrix is the impedance matrix, right? So what we've got is you've got some arbitrary two-port network. So for example, just anything that's got a single input and a single output, right? So how it works is this impedance matrix, right? So just like with Ohm's law, right? V equals I times your impedance. So if you set it up in matrix form instead, you've got V1 and V2, right? So your the voltage at port 1 and the voltage at port 2 is going to be equal to some impedance matrix times the currents, right? So here's just a more compact version of representing them here. And then of course there's the opposite direction, if you want to call it that, the inverse of that, which is the admittance matrix, which is the Y matrix. So same general concept. All you're doing is you're just inverting them. So you're taking the inverse here of Z, and then you get Y, right? So Z is equal to the Z matrix is equal to the inverse of the Y matrix. Same sort of deal, right? So you've got some 4-element matrix here. You perform matrix multiplication, and you'll get your answer. So the main question is how you go about constructing these matrices, right? So you need to be able to somehow determine all 4 elements in the Z or Y matrix in order to, or in the ABCD matrix, which we'll also cover, that you see right at the very bottom of your screen there, in order to be able to use them, right? You need to know what you're multiplying your currents by, or in the case of the Y matrix, what you're multiplying your voltages by, in order to get your respective answers. So if you can model your two-port network, right, as either a T network or a pi network, you can then solve for your variables here, right? So if you've got your matrix, right, Z11, Z12, Z21, and Z22, and you've got your T network or your pi network, and if you represent it in this sort of fashion here, right, where you've got a series, a shunt, and a series element, or a shunt, series, and shunt element, you can take those values and then pop them into your matrices, right? So if you see this one right here is Z11 minus Z12, Z22 minus Z12, and then the shunt is Z12. And also it should be noted that both of these matrices are symmetric. So Z12 is equal to Z21, and Y12 is equal to Y21. Right? So if you do it in either of these fashions, then you can go ahead and solve for them. But of course, do note that Y is of course not impedance; it's the admittance, right, of those elements. So You just have to make sure that you're not just willy-nilly mixing and matching these two together. So moving on, the third matrix that I talked about was the ABCD network, all right? So this is similar in construction, right? But it's just going to be just slightly different. So before we were talking about using both input or using both ports currents to get both voltages, or both voltages to get both currents. Now, typically you won't know that though. You might know what your inputs are, right, at one port, and you want to know what the outputs are at port 2. So for example, with the ABCD network, you can use the voltage and current at port 2 multiplied by the network or the matrix to determine the voltage and current at port 1. So this allows you to also do very simple network cascading too, because what it is that then if you've got some network, right, I'm just representing it by these blocks with ABCD on them, right? So you've got some input, I1 and V1, and it's got an output. And then that output, though, is going to be the input to the next network. And then you've got an output there, right? So all you're doing now is if you were to go through, right? So if you're saying that that our input here is going to be, so port 1, right? So this is port 1, port 2, port 3, port 4. You can solve for what port 4 is depending on port 1 by setting these two ports equal to each other. So we write down our equation for our first network, right? Exactly the same as here. We're just writing it down here. And then we're saying here's the one for the second network, right? And then if you just set these two vectors, this vector and this vector, equal to each other, you get this representation right here. So port 1 is going to be equal to the cascade of both of these ABCD matrices, matrix multiplied with each other, of course, with port 4 right here. And therefore, our resultant ABCD matrix for the two networks cascaded with each other is just the matrix multiplication of those two together. So you can take multiple networks, cascade them all together, and get a single matrix that represents your entire system. So this brings us to the scattering matrix. So things need to be a little bit different for high frequency work, right? Because we need to preserve reflections and transmissions. And that's exactly what the scattering matrix is going to be. You've got some incident wave and some reflected wave at port 1, and some incident wave and reflected wave at port 2. And so note that this isn't like positive terminal and negative terminal or anything like that. This is just this is one port, this is another port. So you've got an incident wave and reflected wave for both ports. So what we can do is we can say that the reflected wave at ports 1 and 2 is going to be equal to the scattering matrix times the incident waves at port 1 and port 2, which makes sense, right? You've got some mathematical representation of saying what fraction of the incident waves are going to be then coming out of your ports 1 and port 2. And I say coming out of, right? Not necessarily just reflected waves, right? I suppose I should clarify that by saying that this wave right here is the wave that is leaving port 1, and this is the one that's leaving port 2. It's not necessarily just reflections, right? For example, if there is no reflection here at port 1, so V1 plus will go through your network and perhaps come out port 2, right? So then V2 minus is going to be proportional to the input here, and of course to the reflection coefficient at port 1. So what we can do is we can say in equation form V1 minus, so the output of port 1 is going to be equal to the reflection of the input of port 1 plus the transmission from port 2. And then by symmetry, the output of port 2 is going to be equal to the transmission from port 1 plus the reflection from port 2. So let's say that the input from port 2 is 0. So port 2 is matched. It has some sort of resistive load attached to it that is of matched impedance to your transmission line, okay? So let's say if you've got a 50 ohm transmission line, port 2 is being terminated by a 50 ohm load. So what do we get from that? Well, we get that the output from port 1 is going to be equal to just the reflection coefficient times the input at port 1. And the output from port 2 is just going to be the transmission from port 1. Okay? So because if port 2 is matched, there's no input, there's no actively driven input ever, and of course there's no reflections either. So you can assume that then V2 plus is 0. So you just put V2 plus is 0, and that's what you get. What does that give you, right? So in this situation, if port 2 is matched, S11 is the reflection coefficient at port 1 when port 2 is matched. S21 is the transmission coefficient at port 1 when port 2 is matched. And similarly for S22 and S12 by symmetry. So what kind of characteristics can a scattering matrix have? Well, if you have a reciprocal network, that means that S12 is equal to S21. So that means that that the transmission from port 1 to port 2 is going to be equal to the transmission from port 2 to port 1. That makes it a reciprocal network. You can have lossless networks, which, if you were to do the math, means that the scattering matrix satisfies the condition where S transpose times S conjugate is equal to identity. This is also known as the unitary condition in linear algebra. A lossless network does not lose power in resistive elements within it. So what's another way of writing that last equation there? Well, here we go. So the magnitude of S11 squared plus the magnitude of S21 squared is equal to 1. And similarly for S12 and S22. If that is satisfied, then you have a lossless network. Here's another example. So if you write it then again, so S11 times S12 conjugate plus S21, S22 conjugate is equal to 0. Again, if that is satisfied, then you have a lossless network. So here's a little proof for it. So if we're saying that it's a lossless network, it means that the total incident power is going to be equal to the total reflected or output power. So in which case then you've got all this going on. You can go through this if you want. You can pause the video right here and take a look at the math. I'll scroll it up a little bit there. This is the end of it. So there you go. So we can also talk about things like port extension onto a network that has been defined by a scattering matrix. So this right here, this just represents some two-port network that we have the scattering matrix for. In addition, we've got two pieces of transmission line attached to both of those networks. We've got L1 and L2, so lengths L1 and length L2. And we've also got, so the scattering matrix is going to have V1 and V2 plus and minus at ports 1 and port 2. And then the cable length, we have W1 plus and minus at the end of the cable, or at the end of the transmission line, and W2 plus and minus at the end of the L2, or at the end of the port 2 transmission line. So what you can do with that is that, again, you can go through and you can determine the effect that that these cables have on your signals that are going into it, right? So, for example, right, you've got your reflected signals coming out of so ignoring the transmission lines again, right, is going to be your scattering matrix times your incident ones. But we've also got the effect that the cable has, right? And the cable, assuming that it is relatively lossless, right, it's going to introduce a phase shift on your signals coming in, right? So it's going to introduce a complex factor right here. So V1 plus, right, so the incident wave at port V1 is going to be equal to the incident wave here, W1 plus, times e to the minus j beta L1, where L1 is, again, the length of that transmission line. So we can go ahead and we can just replace beta Li, where I is either 1 or 2 in this scenario, with theta I. So we can just say that W1 plus, so V1 plus is equal to W1 plus times e to the minus j theta I. And of course this is engineering, so we're using j instead of I for our complex number. And we can write this out for all of them, right? So we've got V1 plus, V2 plus, in terms of W1 plus and W2 plus, and then we've got our reflected wave W1 minus and W2 minus in terms of V1 minus and V2 minus, right? So because the wave, it goes from here, receives an effect from the transmission line. Some amount of it is reflected, some amount of it is outputted from our scattering matrix, and then goes under an effect again by the transmission line. So writing this down then in matrix form by taking all of our equations here and condensing them, we get that V1 minus and V2 minus is equal to this matrix right here, which is just a diagonal matrix, times W1 minus and W2 minus. And in addition, we've got V1 plus and V2 plus is equal to this matrix, which is almost the same as this. It's just got a minus sign in the exponentials there, times W1, or times the vector W1 plus and W2 plus. We can also take this matrix right here, and we can say that it is equal to the scattering matrix times this matrix instead, times this, right? Because what we're doing is we're effectively replacing this vector right here, right? This vector, W1 minus and W2 minus, by these equations right here, and factoring out the minus sign and whatnot. So we get the scattering matrix times this one times that vector. So condensing this all together, what do we end with? Well, our resultant reflected waves, so at the ends of those transmission lines, right? W1 minus and W2 minus, go back in the video if you need to refresh yourself as to exactly where those signals are being measured, is going to be equal to our new scattering matrix times the inputs at the ends of those transmission lines, right? So what we're saying is we've got the impact of the transmission line once, then it hits hits your actual network, right? So you've got the impact of the transmission line once, hits your scattering matrix, right, which is just the mathematical representation of some two-port network in this case, and then as it travels through your transmission line again, it receives another phase shift, and then we get our resultant measurable W1 minus and W2 minus. And with that, this is where I'm going to call it for today's episode. Next time we're going to be taking a look at the input reflection of a two-port network. You can see a little bit on your screen there as to what we're going to be talking about. But it's going to revolve around now bringing back in gamma and using it to help determine or use it to determine gamma from your scattering matrix and different sorts of things and whatnot. But we're going to save that for next time because I promised that we were going to try to keep these videos a little shorter. And also, this day went out to about, I think, 5 pages or so. So definitely do not want to keep dragging this on. So I hope you guys enjoyed the video. Give it the big old thumbs up. Hope I did better than last time. Again, as usual, leave any comments, questions, or concerns or whatnot in the comment section below. Subscribe if you haven't already, if you are interested in seeing more. And I will see you all next time.